But yeah, here we're going to start. So thank you all for being here. We are super excited to host our first multimodal search event, which will be on OpenAI, an intro to OpenAI's CLIP, featuring Sujit Pal, Raphael Pisoni, and James Briggs. Sujit is the technology research director at Elsevier. Elsevier, not sure how you prefer to pronounce that.
Elsevier, yeah.
Great. Raphael is a senior computer vision engineer at Partium, and James Briggs is our staff developer advocate here at Pinecone. And I'm another developer advocate here at Pinecone. If we go to the next slide, we'll talk about our agenda. As I mentioned at the outset, we will be sharing the recording, slide deck, and demos from here in our follow-up email that you will receive after this. Please put all questions in the Q&A box at the bottom of your screen. Don't put your questions in the chat, as they'll probably get missed since the chat is usually rather active, but folks will be responding to questions throughout if they're able, and then during the question and answer period at the end. And with that, I will turn it over to James to kick us off.
Cool, thank you, Sophie. So I'm going to start by giving a quick sort of 101 introduction to vector search. So first thing I want to talk about is, how do we typically, or how do we traditionally compare items? So with text, a lot of this is based on term matching. So given a specific search term or search query, you're essentially going through your query, picking out the different terms within that query, and looking through a database of sentences or paragraphs, and identifying the items where your particular query terms appear the most. You're basically looking for the most frequent overlap of terms. And for images, we can do the same thing. So if you manually add metadata to text, text metadata to images, you can do the same thing. You can search, and it's just going to pull up the text metadata and then display the image that is in front of that text metadata. You have things like color histograms, so you're basically comparing the color profiles of different images, bag of visual words, which literally you can imagine that as having visual words and looking for the overlap between them. But all of these, if we can go on to the next slide, all of these rely on us knowing exactly what we are looking for, or being able to define very specifically very abstract ideas or concepts. And that is generally not intuitive for us as human beings. Our minds work with very abstract ideas, and trying to convert those abstract ideas into very concrete and solid terms, which then a computer can search through in this traditional way, is not ideal. It doesn't, those two modes don't really fit together or translate very easily. So in order to make search more intuitive, you essentially need a way of embedding the human meaning into the things that you're searching for, and also the query that you're searching with. Go on to the next slide. So if we think about the different ways of searching I just described, so the first one was term matching. I'm using this example from Neil Dryman's at one of our previous webinars. So this is using a real example that he ran through, and we were looking for what is the capital of the United States, and using the lexical search, which is a traditional term matching approach, as I just mentioned. The top three results you're getting here, they're just looking at the words and the overlap. So you've got capital United States, and even though all of these items, all these records return context or paragraphs with those words inside them, they are not actually answering the question, because the term matching does not understand the human question behind all of these terms. It's just literally looking at the terms and trying to find the overlap. Whereas if we go for a more meaningful search, a more human-centric search, we would get the results on the right. So we have Washington DC is the capital of the United States, right? So that straight away answers the question. Number two is I was talking about the definition of a capital city. And then the third one is, this is actually another interesting part of this more meaningful semantic search. Even though we don't have the word capital spelled like this, it actually identifies that these two are kind of similar and pulls that in as well. So the more semantic search just allows us to focus more on the meaning. So we can also apply the same to images, right? So on the, recently I've been working with some very small subset of Unsplash images. So on the left, you can see the result from the Unsplash website for a very happy, fluffy animal. So with this query, you can see that there's not really any specific words. And the way that the Unsplash search, or the way that I believe it works, is based on term matching. So the sort of method, so the photographers that upload these images, they have to put a small description. And when we search, it's basically going to try and find metadata that overlaps with our particular search query. And we can see that that mode of searching doesn't really return what we're looking for, which is a very happy, fluffy animal. The very first result seems good, but then the rest of them, the animals don't look very happy. Whereas on the right, you can see a little experiment that I built very quickly using a clip, which is a model we're going to talk about today. And immediately you can see that the meaning behind that query has been captured much more accurately. Like all of these pictures show a fluffy animal and they all look very happy. And this is interesting because this is also a smaller subset of data. So you would think that there's less relevant data in there to be retrieved. And as well, this was just built super quickly. This did not take me long to build. But because we're using the clip model, which focuses on understanding the context within an image, you get immediately more accurate or more human results. Go on to the next slide. So the way that this works, just at a very high level, is you have an embedding model. So in this case, we're going to talk about clip, and you feed in your images, your text, and this can be the database that you're going to be searching through, or it can be a query, and it will output the dense vector embeddings. So vector representations where images and text that are conceptually similar will be placed within a similar vector space. So the distance or the similarity between those vectors will be much higher. Whereas the similarity between very different images and text will be much less. So you can see this here. So in the on the left, you have an image of a dog, and then you have very happy, fluffy animals, and those both get encoded into a similar vector space. They're not exactly the same, but they're similar. Whereas the other piece of text, which is two dogs running across a grassy field, that's not really as relevant to our image. So that kind of gets pushed away a little bit more. Can we move on to the next slide? And once you've created those embeddings, those vector embeddings, you essentially have like a big vector space full of these data points. And so data points map to an image or a piece of text or something else. And what you can do is then use vector search to, given a particular query, you place your query within that vector space, and then you identify the already the other points that are already within that database that are nearest to your query. And then what you return from that is the most relevant results based on the human meaning behind them. Go on to the next slide. And that all of that together is the sort of backbone behind meaningful search. And this here is just almost like a very quick visual that kind of describes that process. So you have the indexing of creating these vectors. You store them in your vector database like Pinecone, and then you, or a user will query, that will create a query vector, and then using that query vector, you return a set of relevant results back to the user. So that's just a very high level introduction to vector search. To give a little bit of context behind the rest of this presentation. So I will hand it over to Raphael.
Thanks, James. So I'm gonna give you a quick introduction to myself. My name is Raphael. I'm a machine learning and computer vision engineer. And in my free time, I love to play with image augmentations or crazy ideas around depth estimation or language models or multimodal search, or play with crazy architectures. If you wanna check some of those recent things out, maybe go to my website or follow me on Twitter. I'm also, again, gonna give you a really quick introduction to Clip. Clip is this really cool model developed by OpenAI. It's trained on images and their corresponding captions, and it tries to place the embeddings of the images and the corresponding captions very close together, while trying, again, to push all the other embeddings of not corresponding images or captions as far away as possible. And if you do that with enough data and train it for long enough, you will find that this creates some semantic clusters in this embedding space. And that actually has a couple of really interesting use cases. One of the use cases definitely is searching. So you can use Clip for search by embedding all of the texts and images that you want to make searchable. You can then add these embeddings to a catalog or to some vector search database. And then once you have a query, you can retrieve similar images or texts or relevant images or texts to this query by embedding the query with Clip again, and then finding the most similar embeddings, just like James just explained. Usually, or in our case, we did this with a similarity metric called cosine similarity, but you can also use some more memory efficient approximations of that, or completely different vector similarity metrics altogether. So on the right, you can see that, just to explain this again, the image of a cute dog and the description, a cute dog, should fall in the space very close to each other in terms of this angular similarity or cosine similarity. And on the other hand, you will see that a submarine and the description, a submarine, also will fall very close to each other, but very on the far end to the dog, because they are very different. And then if we maybe think about some fantasy, or like use some fantasy, we can imagine that maybe the seal will fall in between the two because it has some features that are similar to both of them. This is just a really simple example, but I think it might make things a bit more clear. So some other features of those Clip embeddings are that they have semantic meaning. So they can encode some things that appear in both images and the text. So some things or some concepts that appear in both images and texts will be encoded in these embeddings. So apart from search, you can use those embeddings also, for example, for image captioning for image generation or for zero-shot detection, or maybe for something completely different that you might come up with. So yeah, some really cool things are happening with these clip embeddings. On the right, you can see an example, the example of DALL-E Mini, which is some model that generates images from text. And internally, this model also uses clip embeddings to represent the text and to create images that are similar to this text or to this text embedding. But there is a problem because the original clip was only trained on pairs of images and English texts. So you might want to use clip with a completely different language, or you might want to use it for a completely different target domain that the original clip was not trained for, or you might want to use it with a completely different modality besides images or text. So in the next few slides or in the next presentations, we will show you how you can get around that and how you can train clip with your own model, with your own data. And that's going to be the two clip use cases that me and Sujit will talk about today. So I will talk to you about a model that was developed during the JAX Community Week, organized by Hugging Face and Google around a year ago. And our goal during this community week was to bring clip to the Italian language. We were a team of 6 people that worked on this. Our goal, again, was to train a version of clip that understands Italian while maintaining as much as possible of the original performance. Because at the time there was basically no good Italian clip model. So during that task, we learned a couple things, and I'm gonna tell you about those things. One was that you need to keep as much as possible of the original model. You should make heavy use of pre-training. You should, like the data quality that you train with really matters. And finally, I'm gonna share a couple of tips and tricks with you that we found out during training. So regarding keeping as much as possible, that's really useful because the original clip model was trained on 256 GPUs for 2 weeks. And we really don't want to waste all of that. And so if you want to train a clip model with a different language, then you should really keep as much as possible, which is, in this case, you need to keep the image model because that already knows a lot. And you can just switch out the language model and not replace all of it, or not train everything from scratch. So instead of the original text embedding model, we used a great BERT model that was pre-trained on Italian text by the Bavarian State Library. This was really great because they published it on the Hugging Face Hub. So we could just switch this in instead of the original text embedding model. And it was already pre-trained, which was super useful and actually gave us a great performance boost. Also, another problem around our setting was that in between the image embedding model and the text embedding model, there are 2 reprojection layers that are there to bring the outputs of both models to the same dimensionality. And unfortunately, in our case, they were not aligned and were basically initialized randomly. So that meant that at the start of the training, we had really large and messy gradients that not only were there to train the embedding, the reprojection layers, but they also messed with the original pre-trained models. And that's something that we actually didn't want, because that actually decreased the performance of the original pre-trained models. So the way we fixed that was that we basically froze both the embedding models and basically didn't let the gradients flow from the reprojection layers to the to the original embedding models. And so we were able to basically align the reprojection layers before we started training the entire models. So that means that in the end, after this alignment process, we had much smoother and better gradients for fine-tuning the backbones then. Then regarding the data quality, so the original clip was trained on 400 million image caption pairs. And compared to that, we worked in an extreme low resource setting, because we were never gonna have that amount of data for the Italian language. So first we used the Wikipedia image and text dataset for the Italian portion of Wikipedia. But as you know, many articles and many images in Wikipedia just show a person and its name, or some very technical things with some very technical description. And we were afraid that that wouldn't be a very good data set to train an Italian clip on. So we added an Italian translated version of MS Coco, and that was just 100,000 image and text pairs, but it already showed big improvements during the training. So we were able to show, or to see, that even this relatively small portion of better data would improve the performance a lot. So we said, okay, what can we do to improve the data quality even more? And we added a portion of 700,000 image and text pairs from conceptual captions that we translated with free DeepL accounts. And we were really grateful to DeepL that they have a free tier. But this actually gave us 700,000 translated conceptual captions, and that was actually super useful and improved the quality of the model again by a large margin. And finally, we added some 30,000 image text pairs from the image of the day, or from some image of the day of an Italian newspaper. And they were not many, but they were really useful because they actually contained like native Italian captions, which was really useful. So in the end, we had 1.4 million Italian image caption pairs. That was still far from the 400 million that OpenAI was working with, but we saw that the data quality made a huge difference. And this is something that is basically no surprise, but still was very good to confirm that. And finally, I'm going to show like a couple tips and tricks with you. Some of those might be obvious, but they were still very useful to train this model. The first is don't use Adam with weight decay, because since we were using pre-trained models, we didn't want to decay the weights of the original pre-trained models, because that would have decreased the original weights the longer we train. And that would have been really bad, because we wanted to keep as much as possible of the original performance. So instead of Adam with weight decay, you can just use Adam, or this custom optimizer that we came up with during the competition, and that worked really well. The second tip or trick is again something pretty obvious, but it's to always augment your data. We had, as you see on the right side, we had some pretty crazy image augmentation pipeline, and that helped us to learn more from this small amount of data that we had. So that was really useful. We also wanted to add some text augmentations, but mostly due to the lack of time, we didn't manage to do that during the competition. But still, I mean, we should have augmented also the text, but yeah, always augment your data. That's really useful. And then another pretty obvious tip is to use the biggest batch size that you can fit. This is common practice, but it's even more important for clip, because the bigger the batch size, the more negative examples you will have in the batch. And especially the more hard negative examples you will have in the batch. So that means that from a single batch, the model can learn much more if there is a big batch with a couple hard negative examples. Instead, from a small batch, it just can't learn this much because the probability of hard negative examples will be much smaller. Alternatively, you can use hard negative mining, which also should work really well. But again, we didn't have time to do that. So yeah, would have been really cool. And finally, I want to say something about the clip loss. The original clip was trained with a contrastive loss. And we used that contrastive loss with a fixed logit scale. This logit scale is usually learned, but we fixed it at some almost random value or some empirical value that we found to work really well, and it sped up our training quite significantly. I want to say that the clip loss today is a little bit controversial. One reason for that is that it pushes away all embeddings, no matter how far or close they are to the query embedding. So that might cause some instability or some kind of wiggle of the semantic clusters. And today, I would say that there are better losses in general that can be used. One example can be found at this link, but there are others out there. And finally, once we had the model trained, we really wanted to evaluate it to see if we had succeeded in our venture to create the best Italian clip model out there. We tested the model in two settings. One was the image retrieval setting, where you basically give the model as a query an image description, and you need to find the correct image in a huge catalog of images. And you can see that there we beat mClip. mClip is a model, a multilingual clip version by Niels Reimers that also understands Italian. It was trained with a completely different approach of multilingual knowledge distillation, which is also a really interesting approach. But we were able to show that our model could beat this mClip. And also in the zero-shot classification setting, we were able to beat mClip. Zero-shot classification basically means that you give the model an image and it needs to assign it to text embeddings of different classes. And yeah, as I said, also there we were able to beat mClip on ImageNet, which was really exciting. And we were really happy about those results. And as a bonus result, we were able to create some algorithm that is able to localize the relevant portion of an image in a couple forward passes. And you can basically find relevant portions of the image given a specific text entry. And as you can see in this image or in this graphic, that it works pretty well in some settings, and it would be really cool to work further on that. Yeah, this was really exciting also because this was quite novel at the time. So now it's demo time. Before I show the demo, I really just want to highlight that once you have the slides, you will see that a link to the demo is here, and here is a link to the GitHub repo. So if you want to see what we did exactly, or if you want to retrain this model with a different language, then you can do that with our code. And now I'm going to show you the demo. On the first page of the demo, there is just a really long description of what we did. I'm going to skip that and jump to the second page of the demo directly. And here you can see that you will be able to search for images in the conceptual captions dataset via text query, via an Italian text query. And during the first search, I will search for a cute cat in Italian, of course. would say it's pretty successful. Let's try something else real quick. I'm gonna search for 2 dogs. And again, with this simple query, it's super successful. It finds 2 dogs. And what if we look for something more specific or more special that might not exist in every image data set, or that might be difficult to find? Let's try to find a cat at sundown. Excellent. So we can see a cat at sundown, something you might otherwise not find easily, but this model found it pretty easily. So the next part of the demo will just show you how to do this 0-shot classification. Basically, we can give it a couple labels, and we want the model to classify this into the labels. First, we're gonna give it a cat as a label. And then we're gonna give it a dog as a label. And then we want it to classify. And you can see that the probability of it being a cat is much higher. So I hope that convinces you. And finally, I'm gonna give you a quick demo of the localization demo. Here you can basically find where in the image a specific concept is located. So if we say, okay, in this image, we want to find the cat, and then we locate it. It takes a moment, but we should be able to know on which side the cat is. Excellent. So we can see that the model clearly sees the cat on the left side. And what if we enter a dog? Taking longer than expected? No, it actually works. That's great. Okay, and that's the end of my demo and the end of my presentation. Now I will hand over to Sujit, who also has a really cool use case to share.
Thanks, Raphael. Let me start sharing my screen. Desktop 1. All right, so then slideshow. Yeah. All right, so before we start, I wanted to say thank you for joining me today and joining us all, and wanted to introduce myself. My name is Sujit Pal. I work for Elsevier Labs. My title is Technology Research Director, but it's a bit of a misnomer since I don't actually direct anybody or anything. I'm an individual contributor specializing in search, NLP, and machine learning. In a previous life, I used to be a search engineer working on Solr and Lucene. But nowadays, I work more on the periphery of search and other content pipelines, looking for ways to improve specific aspects of these using machine learning. So a little bit about the project that our team worked on. It is the same as Raphael mentioned. This is the Jax Flax Community Week, organized by Hugging Face and sponsored also by Google Cloud. They gave us TPU time. And honestly, our project is probably in some ways less innovative than Raphael's, but I think it will resonate more with more people in the sense that image search, it's something that everybody does, or everybody wants to do well. So in that sense, we use Clip for image search on satellite images. And the requirement for the community week was that we had to take a JAX model, the transformer model on Hugging Face, and do something with it, right? And we basically chose to work on Clip and also if you don't know, JAX is basically like NumPy, but optimized for use on GPUs and TPUs. Yeah, so that, and Flax is a neural network library built on top of JAX. So for us, honestly, the lure of working on TPUs was actually a bigger draw for us than actually, fine-tuning CLIP in general, right? So it was like we were kind of drawn to it more for the TPU aspect of it, the chance to work with TPUs. So what we did was we basically fine-tuned OpenAI CLIP for satellite images and used it to power an image search application, right? Here is our team. We basically are all from the 2EML Slack channel. 2EML stands for This Week in Machine Learning. It used to be a podcast in machine learning. It still is, organized by, which is run by the founder of 2EML. But mostly it's a Slack channel now with people from different parts, different companies coming to engage together around ML and ML-like things, right? So basically that's how we met the team here. Left to right, Arto, he basically did most of the work on fine-tuning the model. He basically led the thing. Dev did some initial work on the data preparation. Gautam, he did he did actually all the work on the caption augmentation part using back translation. Mayank, well, he brought us news of this contest as well as worked on the fine-tuning. Rito also worked on the fine-tuning, and I basically worked on some image augmentation and the demo, right? So that's basically what we did. And we did not have a lot of central coordination. People just pitched in to do what they could and where they could help. And ultimately, everything just clicked together, and we came in third on this thing. And so, lots of respect to all my teammates for their great work, right? So, so the question is, somebody raised it on the chat as well. Why fine tune, right? I mean, Raphael already talked about the CLIP training regime, right? 2 weeks on 256 GPUs, 400 million image text pairs, right? And James talked about how good it is at zero-shot learning, even, right? And that is true. CLIP is really good on at like as it is, as out of the box, basically, on natural images, like images that you can see when you look around you, right? And it's not surprising, I mean, given the large number of image text pairs, right? However, CLIP does not do very well with images that are from some specialized domain. We have noticed this on satellite images. So with satellite images, your perspective is different, right? You're looking, from the top down. We have also seen it in medical images. You have the same issue. So as you can see here, we did a little evaluation. And sorry for flipping the script, but I wanted to kind of bring this up ahead of time, just to make sure kind of give you a rationale for why we did the work, right? So we, out of the box OpenAI CLIP on our test set of satellite image text pairs, it gives you a recall at 1 of 0.57 and recall at 10 of 0.93, I think. Yeah, 0.93. Yeah. And after we fine-tuned, our best model has a recall at 1 of 0.88 and 0.99 respectively. So, obviously, so the answer, I guess, is that, if your images are not natural images, then fine-tuning CLIP can take your results from, decent to, pretty much spectacular, right? So that would be, that is our rationale, basically. For our data set, we used the RSICD data set. This is an open source data set for remote sensing and satellite imagery. It has about 10,000 images, 224 by 224 pixel images, and approximately 5 sentences, for its captions, right? So each image has around 5 captions, around a sentence long. And we augmented it with additional data sets from the UCM data set, which had around 2,100 images, and the Sydney data set, which had around 600 images. And basically, these have the same kind of ratio, approximately 5 captions per image. So, and you can see some examples of the kind of images we are talking about here, right? So this is like a residential area. This is an airport, and these are the runways here. This is a meadow. This is like a river going through a city, right? And this is like a resort taken from an aerial image taken from a resort. But even though we had quite a bit of data and fine tuning, honestly, we are doing fine tuning, right? So we don't need as much data as the original pre-training. But even though, and so the one thing that actually prompted us to do the augmentation was that with TPUs, our training runs went like really fast, right? So what would normally take 2 to 3 hours on a GPU would go, finish in like 15 minutes, right? So we basically said, let's add more data and see if we can improve it, right? So we did both caption augmentation and image augmentation. So for the caption augmentation, we use back translation. So you can see it here, right? So essentially what it is you take the English text, you transform it into, or translate it into some language, and then you translate it back to English, right? So you can see it for English and French. So, the source caption was image of a ball field in Baltimore, and the one that comes back after back translation is image of a Baltimore ballpark. Subtly different, but it's the same thing, right? Similarly with image augmentation. Oh, and we went through 5 different languages to do this. And we used the Hugging Face MarianMT project, which is a set of translators, pre-trained translators for common languages. And we took 5 of them, and then we just worked with that. And for image translation, we used standard torch vision, standard transforms from the torch vision project. Essentially, what we do is we basically hook up a bunch of like a sequence of transforms, and we call them randomly, right? So so per batch we decide what the sequence should be, and we pass in the image through it. And this is done, inline with the thing, because we don't want to store images, so we just do it inline. For the captions augmentation, we basically did it offline because we are talking about big models here, which had to be called, and we had to run predictions on those, right? Okay. So this was all there was. Okay, for the fine tuning part, Raphael mentioned contrastive learning. Essentially, all it is you pass in, you tell the model what positive pairs look like and what negative pairs look like, right? And your contrastive loss function would try to, pull together positive pairs, positive pair examples, and push further apart the negative pair examples, right? So here, as you can see, you pass in the caption and the corresponding image as batches via the text encoder and the image encoder. And essentially what you have is a matrix of pairs, right? So if you can visualize them as a matrix. Anything that is along the diagonal are all positive pairs. Anything that is off diagonal are all negative pairs. And you can sample from the negative pairs to create as big a negative, you can mine this basically, right? Mine the off diagonal things for negative pairs. And the idea is very similar to, what's that called? Support vector machines, right? Where you're trying to kind of, create a margin, right? So that margin separates the, the negatives from the positives, right? So it's kind of similar. If you look at the contrastive loss function, somebody mentioned Lilian Wang's blog, so I think we can look at that. Basically, it's that there are 2 parts, and it's basically trying to push the 2, the positives and the negatives, and keep a broad enough margin, right? So so it's easy to differentiate between the 2. And again, so I think our batch size was also quite large. We used a batch size of 1024. So we had TPUs, so 8 cores, and 128 per, we took 128 pairs per TPU core. And so we had like 1024. Our best model used the Adam optimizer with, learning rate was 5e-6 with linear decay. You can download a model from Hugging Face, and you can access our training code on GitHub in case you want to reproduce it or look at what we did, right? And and finally, so I'm just going to give you a little overview of the demo. We will cover this in the demo. So essentially, it's an application of our fine-tuned clip model. So we supported text to image search, image to image search, and identify landmarks in image. And you will see they're largely very similar to what Raphael showed you as well, right? At index time, we took all our, the image, we calculated image embeddings for all our images, and we put them in a vector database. You could use something like Pinecone, for instance, and at query time, you take in the text of the query, you compute the embedding using the clip model, and then you find approximate nearest neighbors using your vector database and return them ordered by nearness, right? So that's basically all it is. So I'm going to just go and do the. I hope you can see this, right? This demo. Yeah.
Yeah, we can see it.
Okay. Okay. So again, the demo has 3 parts. So we can retrieve images given text. So you could do, so we have some canned stuff here. Like you can, look at, say, maybe, ships, right? And so you can see images of ships. It's and correspondingly, these are the captions that are associated with it. Or for instance, maybe beaches, right? So you could, see, things like that. Or you could even say, baseball fields, right? So let's say baseball fields. And so that will give you like, different aerial shots of baseball fields, right? So this is like, given a text, and this is like basically what you would think of at image search, right? In terms of Google, right? You enter something and you click images and that's what you get, right? So slightly different is, when you provide an image and you expect to see similar images. Again, we have some canned images here. So, you can look for maybe, image 8, right? Whatever. This is like, it's a commercial, buildings, right? So it's got different, types of images of buildings. Or you could look for, like something else. It's not, I think what this is, I'm not sure what this is. Oh, these are the airports. Okay. Or you could basically pick something off the internet and you could basically provide an image URL to it. So we have one here. And, this is like, very densely populated seaside, area, right? So you can see the sea here and you can see all the densely populated areas here. And you get back results, which are not, that great. These are like not as populated, you would think, right? But this, or maybe this is actually farmland. So, so anyway, so this is what we get, right? And then you have the feature in feature, which is essentially, again, very similar to the dog and cat example Raphael showed. Essentially what this is that, given an image which you provide, you can identify, you can ask the model to identify the areas in that image where you have described, in text what you want to see, right? So here in this image, this is the image of Saint Tropez, and you want to see maybe the beaches, right? So you can, so you can say Saint Tropez port and then beach, right? And you find it. So what it does is it breaks it up into patches, and so it breaks it up and then categorizes them or orders them basically, right, to see which are the best beach pictures that you got, right? So here it says this is number 1, right? This is number 2. I think this is 4, and this is 3. So it basically took this area and said that this is most likely the beach, right? And it gives you little scores, which are really I think cosine similarities, or yeah, cosine similarities. So another example, similar example, like if you look at a forest with river, for instance, and you say, so, and you say maybe, I have a forest with river, let me look at the rivers, right? So And so you get this image that you get, right? So, here's your forest, here's your river going through. And then it, finds the patches where the river is most likely to exist. And it says like, this is number 1, this is number 2, 3, 4, 5, and 6. So essentially it has followed the path of the river, right? So, this is, this is on satellite images, but you can, kind of envision this on medical images, for instance, and you have, say, maybe X-rays and human, technicians basically trying to look for tumors. You could have the machine identify these tumors, areas where tumors could be ahead of time, and mark it out so that the human can actually, work faster, right? Similarly, for people who are doing geological things or in defense, this could be very, very useful, right? You say, okay, find me the area where these characteristics exist, right? And that's how you would kind of get it. So essentially, this is our demo. And again, thank you for listening so far. And I'll hand back to Sophie. I think I'll stop sharing. Right? Yeah.
Thank you all so much. This was incredibly informative. There are a bunch of questions that people already have in the chat in the Q&A box. Thank you to folks who have been answering them throughout. There are 12 right now, but we can hop right into the first questions and answer them live out loud so people can hear what folks have to say. So the first question is, how can we search among image text pairs given an image text query?
I think we covered that, Surya.
Great.
Yeah. Maybe to give, I don't know how it was meant, but maybe how could we search for something where in the query we have both images and text. So one way to do that would just be to combine the embeddings of the image and the text with some way of combining, maybe just adding or
even averaging would be fine.
Averaging the embeddings, that would be fine, exactly.
Okay, would it be interesting to consider the perceived or real gain in relevant recall? Or this is Hernando's question. Would it be interesting to consider the perceived or real gain in relevant recall for symbolic, semantic versus clip model search? We did not do exactly that, but we could. I mean, we could compare. So, using tagged content, for instance, right? So if you have your images which are tagged with certain keywords and you try to do text search, that's what we have been doing for what we call image search so far. We pre-tag it and then we look for tags. You could find you could measure that, so that would be an interesting thing to measure too. Yes, I think so. But we used recall as well when our as our evaluation metric between the out-of-the-box clip model versus what we fine-tuned as well. So that's a good metric.
The next question is, how did you, so this is from Steve Han, how did you align the image embedding and test embedding so that the same or similar entities embedding the closer and different entities further? So I assume this is the training clip.
Contrastive learning. Right.
Exactly. This is done with some contrastive loss that tries to push corresponding embeddings together and push all other embeddings away. This is, yeah, as Sujit said, contrastive learning, very simple concept. Again, there are different losses to do that, and yeah.
Cool, thank you. One from Sean Wilner. Have you explored VIC reg as a contrastive alternative?
I haven't. Thank you. I mean, I will look at it.
Yeah, same here.
Okay, cool. So from Anonymous, what is the difference between 0-shot, 1-shot, and 2-shot detectors?
So maybe I don't know about detectors, but maybe if we go for zero shot, like to explain the concepts of zero and one shot, and yeah. So if you do zero shot, for example, classification, then you have to classify an image, for example, that you have no example for. So in the case of clip, it would be you search via text for something that the model has never seen during training. So for example, if you say, I want to see a blue cat, and it never has seen any blue cats in the training data set, but it would still be able to identify a blue cat if it sees one for the first time. That basically would be a zero shot setting. One shot setting compared to that would be when you already have an example of an image with a blue cat and you want to find other images of blue cats, then this would be a one shot setting. Yeah, I don't know, Sujit, do you have?
I think that's pretty much, I think of it as zero shot and few shot, right? So
yeah, exactly.
Zero shot is untrained, few shot is like, some amount of training data and it works. So
exactly.
Yeah.
Cool, thanks both. One from Hernando. Hernando, is there a class of tests that would allow a metric between test labels and query versus image class and query? The reason for that being the lowest cost route for semantic adjacency would be text from labels versus query compared to image versus query.
Can I address this?
Yeah.
Okay. So essentially what Clip does is it creates a joint embedding, right? So when you're pushing in this text label and its corresponding image, it tries to push them together close, right? So it's essentially a joint embedding. So if you pass in the text, it'll create an embedding, right? A vector. If you pass in the corresponding image, it will create a vector very similar to that vector, right? So essentially what you are asking here is there. Clip does this, so it's a joint embedding between text and, so multimodal, right? So that's basically the origin of the term, I guess, right? So yeah, so I think I answered your question, but I'm not sure. Yeah.
Sounded good to me.
Okay. Yeah.
Cool. One from Dan Lee. So this is for you, Raphael. You mentioned that the parameters of the text encoder and the image encoder are frozen, and only the linear lay parameters are updated. If this is the case, why does Adam or Adam with weight decay actually? Why does that matter?
I'm really happy that you asked this question, Dan, because this might actually be my fault that I didn't explain this properly. So the way we did it was that we first froze the two backbones and only trained the reprojection layers. And only once the reprojection layers had settled and were aligned to each other, we unfroze the entire model and then trained the entire model. So in that case, that you consider where both the backbones would be frozen, effectively Adam versus Adam with weight decay would not make a difference, or actually Adam with weight decay would be good. But in the case where you have the two backbones unfrozen, then of course you want to preserve the weights of the backbones as much as possible in order to avoid the image model to forgetting what it has learned in the original clip training. So really, thanks for that question, and sorry if I jumped over the explanation too quickly.
Thank you. So next question is from Verqua. Sorry if I'm pronouncing that wrong. You mentioned early that data quality matters. I think this is for you, Raphael. So what if we translated the current English to image caption data set using NLLB? Is it good practice or not?
So if I understand you correctly, you would like to translate the text queries with some language model like No Language Left Behind or some other model to a different language, and then try to train the model on that, or yeah, probably to train the model on that data, on that newly translated data. And that is essentially what we did. So we created 700,000 text queries or text embeddings. Oh, this is about the query? No, I don't think it's about
I think you understood it. That's the way I've understood it.
Yeah, so during training, we essentially machine translated with a translation model a large part of the data set, and actually trained on that. So if you're suggesting that, that is exactly what we did. You could also translate, of course, a query to English, but that depends on how well the translation model works, of course, during inference then.
Thank you. The next one's from Joe. What is the approximate inference time when running Clip on GPU and CPU?
So that depends a lot on your GPU or CPU. I would say that it takes around, I don't know. So on GPU, I would say it takes somewhere between 10 and 100 milliseconds, depending on your GPU, of course. But yeah, and on CPU, it probably takes some more time. Also, it depends on what you want to do, because if you do both image and text embedding, then of course it will take quite some time. While if you only do image embedding or only text embedding, the text model is quite lightweight, or relatively lightweight compared to the image model. So
also for inference, you're, if you're doing things like image search or matching, right? Essentially, you're not using Clip anymore. You're using the vector database, right? So then it would depend on what kind of vector database you have and so forth, right?
Exactly.
You
would only use Clip to embed the query itself.
Exactly.
Then of course all the search would be in the vector database, which would should be really quick. Yeah, exactly.
Right.
Thanks, both. One from Jade. Yeah, I think this is for Sujit. She asked, why do you include natural images only?
We didn't. These are all, well, remote sensing images. The ones you saw are not truly satellite images because they'll be from a further longer distance. But these are all from remote sensing images, and they are, not natural in the sense that if you look around you, you won't see that. You have to be up in a drone somewhere, or somewhere high up and looking downwards. So, and that was the image data set that we had. Yeah. So, and that was the mandate basically. Well, not mandate. We chose our mandate, but we basically did for satellite image and RSICD images basically, right? So, yeah.
Yeah, I think maybe the confusion there is like the original Clip from OpenAI. It's trained on mostly natural images.
Right.
Which is obviously why you needed to fine tune it on your non-natural images.
Right, exactly.
Yeah. Okay. Thanks for that. Another one. From Jazia is
we used the machine translation, and we use pre-trained models from the Marian-MT set of machine translation models. These are also transformer-based models, and they are also hosted in Hugging Face. So we didn't try to train them. We just took them as pre-trained and just used them to do the back translation.
Thank you. So that's for the question. What do you use for text augmentation, machine translation, or human translation? Thank you. The next one is from Kenan, and so this one's for you, Raphael. Is the localization result demo based on bounding boxes, or is it a detailed shape of the object? He's asking this because in the slides, it seems like the cat-specific shape was detected, but on the Hugging Face UI, it seems like it's using a bounding box.
So the approach in the demo and in the slide is actually the same, and it's not based on the bounding box, but it basically subdivides the image into different areas, and it tries through multiple inference steps to find the most relevant area for the specific text query. So this is not based on a bounding box in any case, but it's just, and it's also not trained into the model. This is what we were able to do with the model that was never trained for this task, basically. So yeah, as I said, I'm like quickly gonna repeat it. The image is subdivided, like similar to what Sujit showed in his demo. The image is subdivided into different areas, and it just finds the more relevant areas for a specific concept that is given by text. Yeah, that's it.
Great, thanks. Does the actually just adding on to that, does this the size of these patches, does that change, or is it just a single size that goes across the entire image?
So basically the size changes, yes.
Mm-hmm.
So you cannot divide the image into very small areas, because otherwise the model has no context and doesn't know, okay, should this be part of a cat, because it only sees one really tiny patch of fur. So that's why the size changes, and then the relevance of the individual regions is aggregated with some aggregation function.
Right. Okay, that's cool. Thank you. And then, so next one is from Uchena. So why go through the stress of training Italian clips when you could have used machine translation to convert Italian to English and perform the search?
Yeah, cheeky question. No, I mean, it makes sense, but we were hoping to get better results compared to just simple translation. And I think we actually did. For example, the model that we compared our model to in the end, this M-clip by Neil Trimers, actually did something very similar, where they tried to train a text encoder to output the same embeddings to different different versions in different languages of the same text input. And basically we were able to show that we beat that approach. And I'm confident that we also delivered good results compared to simple translation. So I'm sure that it would also have worked somehow, but I guess that we got pretty decent results as well compared to that. So yeah, we really wanted to try.
Nice, thank you. Another one for you, Raphael, from Dan is, so I think he wants you to expand on the whole Adam weight decay thing. So why is Adam weight decay used instead of Adam?
So actually we used Adam instead of Adam with weight decay, because if you have weight decay, you actually decay the weights of the pre-trained model, so of the original clip image model and also of the pre-trained text model. We would have decayed the weights, and we actually wanted to retain as much knowledge inside of what it had learned of this model without breaking too much with our training. And you can imagine that because we had very little data, we needed to train for quite a significant amount of epochs. And if we would have done that for too long and without augmentations especially, then the model would have completely overfit on this data, and it wouldn't have worked very well in the end. So that's why we tried to keep the weights of the original model as much as possible. We could have even used a smaller learning rate for that or something similar. We actually already used a quite small learning rate. Yeah, we tried to keep the weight as much as possible of the original clip model, and that's why we didn't use weight decay, because that would have decayed the weights. the original model. Yeah.
Cool. Thank you. So another one, so from an anonymous again here. So freezing the backbone decreases the training time. So I think this may be a similar answer. So are there any other benefits when to freeze the backbone, when not to? And also again, asking about atom decay, but I think you've answered that anyway, so skip that bit.
So again, freezing the backbone just keeps the weights as they are while we train the reprojection layers. The reprojection layers in our case were randomly initialized, so that meant that initially we had to mainly train the reprojection layers to transform the output into something that made sense, the output of the backbones into something that made sense, and especially to align the two reprojection layers to output something similar. And that's why we froze the backbones, because the initial training, when the reprojection layers were still messy and randomly initialized, that initial training would have messed a lot with the backbones. So we really didn't want to mess with the backbones too much, and that's why we first froze the backbones, only trained the reprojection layers, and once the reprojection layers were kind of aligned, we unfroze everything and trained everything together. Same reason, or a very similar reason for Adam with weight decay. We didn't want to decay the weights. We didn't want to mess with the backbones that were already doing or already trained.
Cool, thank you. So on to the last few questions now. If anyone else has any more questions, like pop them in the Q&A field now, and we'll try and get around to them. So from Hannah, her use case is more around finding similar images for a image query, so image to image search. So is that a use case that that Clip and or her researching Clip and other similar spaces would be useful for?
If you're not doing any multimodal things, if you're just doing image similarity, it might, you might as well do things like ImageNet, right? Take an ImageNet model, fine tune it for your data, and that should be sufficient for image similarity. It's only when you are trying to mix modalities is where Clip is really useful because of the joint embedding thing, right? This is my opinion, at least. I mean, obviously you could use Clip; it's not impossible, but it would be like using a bulldozer to, well, not a bulldozer, maybe power tool when you don't need one, right? So yeah.
Exactly. Yeah. Maybe to present a counterpoint. The only reason why you would use Clip for purely image search is if you want to find semantic concepts in the images. For example, if you have a hand drawing of a unicorn and you want to find a picture of a more realistic unicorn, then the images might look completely different. But if you still want those two concepts to appear close by, then this semantic aspect of Clip could be very interesting.
Yep. And
that's one case where you would use Clip maybe for pure image search. But again, just as Sujit said, it's a lot of work for something that might not be necessary for your use case.
Right.
Cool. Thank you both. So another one from Anonymous. I heard you use TPUs instead of GPU for model training. So this would be for, I assume, Sujit. Do you use Google Cloud or which cloud solution? I'll let you answer that.
We use GCP. TPUs are available on GCP, and Google Cloud was sponsoring it, and they gave us an account, temporary account. So that's what we used. And did you use Google Cloud? Yes, we did. And model inference for big models, you need to use GPU. Not necessarily, as at least for our use case, we are just, using the trained model to generate the embeddings, and then depending on the vector database to do the approximate nearest neighbor search. So In our case, we didn't need, I can think of maybe cases where we might need GPU, but usually, unless you're talking of really big models, CPUs are good enough for inference, right? Yeah, but again, it depends on the size of your model and how powerful it is and so forth.
But for example, I think that both of our demos are running on CPUs, so
yes,
yeah, I think it's enough for the usual use case.
Cool, thank you. So for you, Raphael, Hannah's asking if Hannah's asking about the caption generation process that you mentioned. If you could expand on that a little bit.
Yeah, I mentioned it offhand because I don't have much experience with it, but honestly, what you can do with these clip embeddings is that you embed an image into this semantic vector, and then you train another model to create or to use this semantic vector as a starting point to create a caption for the model. So these vectors just encode a lot of information, a lot of interesting information about the image, and you can then use this embedding as a starting point for this caption generation. Just like it is done with many other caption generation models, you just have a starting point in the form of a vector.
Cool, thank you. Another one from Steve. So after you train the backbones, and you move on to training the full models, do you need to train the reproduction layers again?
Yeah, basically first we just train the reprojection layers, and then we train everything together. So both the reprojection layers and the backbones. That's basically in the second step then, yeah.
Thank you. And Mo wants to know if you have any thoughts on bringing a third modality into it.
Yeah.
I think there are approaches to do that. There are definitely papers published on that. So yeah, if you want to do that, read the papers. I don't know any of them by heart, but I'm sure there are cool papers out there or cool approaches out there to try that.
Yeah, theoretically it should be possible. Yeah, you have three, and then you would take all three together, and yeah.
I think there are approaches to include audio or even video maybe. So I'm sure it would be possible, and I'm sure there's cool papers out there about that stuff. So yeah, check it out.
Thank you both.
I think it's a repeat.
Yeah, I think it's a repeat question. Okay. So Zach is asking about more abstract images. So for example, the Kandinsky red square, would the houses be identified?
It depends on the training data, I think.
Exactly.
Yeah.
It depends heavily on the training data. If you have a lot of abstract paintings with descriptions in the training data, then the model might understand these abstract concepts. If you only train on natural images and not so much on abstract images, then it's really hard for the model to make any sense of what it's looking at.
Yeah, there was a case, I think I remember, in the art world, right? They did something very similar, where they used these vector embeddings for images to find similar images by the same artist and so forth. So that was actually quite cool. I read about it somewhere, but I don't have references handy.
Great, thank you. So another one is, so from Mo, is asking if someone used Vertex AI, did they use Scan for the serving? I don't know if we did or not.
No, we used the Hugging Faces spaces. That was the platform we are putting our demo on. If you mean, the vector database that we used, I hadn't heard of Pinecone then, so I actually used NMSlib, which is, it is the fastest on CPU, even better than FICE, but FICE is better on GPU. But NMSlib is like an approximate nearest neighbor library that you can use to do vector search. So that's what I used. I don't know what Raphael used.
We actually did know approximate nearest neighbors, since we had like a reasonable amount of data. We had like, I don't know, like the biggest catalog that we had was like 170K images. And we actually did all of that in memory, which is yeah.
Okay, there you go. Yeah.
So it's a huge matrix multiplication for the cosine similarity. So it was not approximate, it was exact, but of course that takes quite some memory, and I guess that Hugging Face is not very happy about us doing that.
Okay, thanks both. Okay. So from Stefanos, he wants to know if you published a paper for the Italian clip.
We actually wrote a paper. It should be on archive. It's it's called. I have to think about the name. It's called. I will add a link to the mail that James will send out after the presentation, and I will let you know about the paper. But there is a paper, you can probably find it with Clip Italian, and it was never published on any conference or anything, but there is a paper, and I hope it's going to be interesting once you see it.
Great, thank you. Another one from Anonymous. So I think you use Streamlit Cache to load the model. What other prototyping tools do you use? And do you use albumentations?
No, we didn't.
PyTorch augmentation.
Yeah. So for our transforms, and so we use PyTorch's Torch Vision project, right? It has a bunch of transforms that it comes out of the box, and we just arrange them in sequences. I'm not sure what Raphael did. This is what we did basically, right?
We did the same thing. We just used Torch Vision. Of course, there's a lot more options in albumentations that would also have been interesting, but for us, Torch Vision was almost more than enough. But of course, there's really cool things in albumentations as well, so that would have been really cool as well. Yeah.
Thank you both. Uchenna had a question on if either of you have suggestions on training a similar model for rare, low resource languages.
So using images as the bridge, right? That would be really cool. So, and I think Raphael, did something similar along those lines, right? So when I looked at Clip Italian, the first thing I saw is, if I ever go to Italy and I don't know Italian, I don't. So I could show pictures and, it would tell me what to say, right? So I think that is a really, really cool application. And, using images as the bridge to bridge the, the high resource language and the low resource language.
Yeah.
I don't have a suggestion, but I think it's a really cool idea.
I think if there is a translation model that gives decent results for this rare language, for this very resource or low resource language, then there is a decent chance to train a clip model that either works with language distillation or knowledge distillation, or to completely train on a translated catalog. But yeah, rare languages or low resource languages are tough. We had 1.4 million image text pairs, and that already was, as I said, quite low resource. So I don't know, if you don't have a good translation model to translate a lot of queries, then that would probably be difficult.
Great. Thank you both. We have just one last question and we'll wrap it up. So from Anonymous again, did you set parameterized hyperparameter search for your augmentations through a continuous to find the best parameters? And is it one augmentation that you train first, or do you just plug in everything due to a lack of time?
We did do without and with, and I think if you look at the list of models we trained, there were some without text augmentation, some without image augmentation. So, and we kept adding things, right? So the ones without augmentation performed poorly, and as we learned how to do it and we added more data, it got better and better. So, but we have results for all of them. So if you look at our website, the GitHub page, you'll find a table with all our results. So we did. Also for hyperparameter search, we used weights and biases to do that. I'm not exactly sure of the details. This was more of Arto's work. So, but I know we did use that. So, yeah.
Great, thank you both. So we'll just end it there.
Thank you all so much.
I'm sorry, yep.
I was going to say, thank you all so much. Thank you, Raphael, James, and Sujit for your presentation, answering so many questions. We really appreciate everyone who attended, and we'll be sending out a follow-up email today or tomorrow with all of the wonderful resources in here, the recording, the demos, and everything you need to utilize CLIP in your work, should you not be doing so already and would like to. Have a great rest of your day, everyone, and see you at our next event on September 15th, which will be featuring graph-based ANN and HNSW. Yuri Malkov, the author of HNSW, and James will be presenting there. So looking forward to seeing you there. Have a wonderful weekend as well.
All right, thanks all.
Great, thank you.
Thanks a lot.
Bye.